All right, let's dive into one of the most important, but kinda invisible, pieces of engineering that powers our entire world, three-phase power. Seriously, this is the unsung hero that keeps everything from giant factories to the grid itself up and running. So let's get into it.
So have you ever been driving along, you look up at those huge transmission towers, and you notice the wires nearly always come in sets of 3? I bet you have. Well, that's not just a coincidence, and it's not for backup either. It's actually a massive clue that points us to the brilliant system we're about to unpack.
The answer to that big question, it all comes down to a really clever and honestly elegant engineering solution called three-phase power. We're going to see how making that jump from 1 wire to 3 just completely changed the game for how we move and use electricity.
At its core, the reason is actually pretty simple. Using 3 phases just lets us deliver way more power, and do it a whole lot more smoothly and efficiently than you ever could with a single phase. The whole system is basically purpose-built for stability and incredible performance.
Okay, to really get how this works, we've got to go right to the source, the generator. This is where all the magic starts, with a design that is, no joke, a masterclass in balance and precision.
You know, the basic principle of any generator is super simple. You just spin a magnet inside a coil of wire. As that magnetic field sweeps past the wire, boom, it creates a current. This gives you a single, simple wave of electricity, what we call single-phase power. It goes up, it goes down. It works, but it's not very smooth.
So how do we level this up? Well, imagine we take that one coil. Then we add a second one and a third one. But here is the absolutely crucial part, the placement. Each of these coils is positioned at a perfect 120-degree angle from the others. That precise physical spacing, that is the key to everything.
And this is the result. It's awesome. Because of that 120-degree spacing, as the magnet spins, it creates a voltage in each coil at a slightly different moment. So the output isn't just one wave anymore. It's 3 identical waves, but each one is perfectly out of sync, or phase shifted from the next, by exactly 1/3 of a cycle. It's like they're in a constant, synchronized dance with each other.
And this brings us to the coolest part of this whole setup. The system is perfectly balanced. Because those 3 waves are so precisely offset, if you were to add up their voltages at any single instant in time, the total is always 0. The positive peaks perfectly cancel out the negative valleys. This incredible balance is the secret to why the whole system is so stable and efficient, and it's why huge 3-phase motors run so unbelievably smoothly.
Okay, so we've generated 3 separate waves of power. Now what do? We have to figure out how to wire them all together to send that power out into the world. And for that, engineers came up with 2 main blueprints, named for the shapes they make, Y and delta.
First up, we've got the Y connection. You'll sometimes hear it called a Y or star connection, and you can picture it exactly like the letter Y. The ends of the 3 coils are all brought together and joined at one single common point. And this point is super important. We call it the neutral.
The other way to do it is the delta connection. In this case, instead of everything meeting in the middle, the 3 coils are connected end to end, and they form a closed triangle, just like the Greek letter delta. And the big, obvious difference here, there's no neutral point in a standard delta configuration.
So what's the real difference in the real world? Well, the Y connection with that neutral wire is incredibly versatile. It's what utility companies use to bring power to our neighborhoods because they need to supply both smaller single-phase loads for our houses and bigger 3-phase loads for businesses. The delta connection, on the other hand, is an absolute powerhouse. It's the go-to choice for running those massive industrial motors that need a high-power, perfectly balanced supply.
Okay, I know this table looks a little intense, but it's really the secret decoder ring for why engineers choose one setup over the other. And you'll see this funny number popping up, the square root of 3. You don't have to do the math, just know that number comes directly from that 120-degree geometry we talked about. Here's the bottom line. In a Y connection, you get a higher voltage on the line. In a delta connection, you get a higher current. It's a trade-off, and it lets engineers match the power supply perfectly to the job it needs to do.
All right, now that we know how it's all hooked up, how do we actually talk about the power flowing through it? Because it's not as simple as just one number. We actually have to break it down into 3 different types of power.
First, there's average power. You might also hear it called real power or true power. Basically, this is the good stuff. It's the workhorse. It's the power that is actually doing useful work. You know, turning a motor, lighting a bulb, making things happen. We measure this in watts.
Then we have something called reactive power.
The best way to think about this is as storage power. It isn't actually doing any real work, but it's absolutely essential for things like motors and transformers that need magnetic fields to operate. It's kind of like energy that's just sloshing back and forth in the system to keep those fields alive. We measure it in VARs.
And finally, there's apparent power. This is the total power. It's the combination of both our workhorse power and that sloshing storage power. It really represents the total load, the total strain on the system. The power company has to be able to generate and send all of this, even the part that isn't doing work, so all the wires and transformers have to be big enough to handle it.
So this brings us to a really crucial idea, the relationship between these different types of power. We measure it with something called the power factor. Think of it as an efficiency score. It's basically the ratio of the real workhorse power to the total apparent power. A perfect score would be 1.0, which means every bit of power being sent is doing useful work. In the example from our source material, the power factor is 0.6. That tells us that only 60% of the total power is actually getting work done. The rest is just that reactive power sloshing around.
And that brings us right back to the beginning. We've seen how this power is made, how it's connected, how we measure it. So let's put it all together and finally answer our original question. Why go through all this trouble? What is the big advantage?
The advantages are just huge. I mean, first off, you get more bang for your buck. You can transmit way more power with less copper wire. The power delivery is also incredibly smooth and constant. None of those peaks and valleys you get with single phase. That's perfect for big motors. The whole balanced system is just naturally more efficient. And get this, it even lets large motors start all by themselves without needing extra complicated circuits. It's just a better design in almost every single way for big jobs.
So, the next time you look up and see those 3 wires strung across the sky, you'll know the secret. You'll know they represent this perfectly balanced, super efficient, and incredibly powerful system that's always working, just behind the scenes. It really makes you wonder, doesn't it? What other amazing, invisible engineering systems are out there, quietly powering our world every day?